Hello, AP Stats. This is the video talking through chapter 23, inferences about means. And in this chapter, we're moving on from proportions and we're moving on to means. And it's going to be more confidence intervals and hypothesis tests, except now we're not trying to capture the true proportion in an interval. Now we're trying to capture the true mean for a population in our interval. So we're going to draw a sample, get a mean from the sample. From that sample mean, we're going to reach out a certain number of standard deviations, try to capture the true mean, and then say we're 90% confident the true mean is between this and that. So we're doing the same thing. There are some differences, but we're just going to do a confidence interval to try to capture a true mean, and then a hypothesis test for a mean. And you can add these two to our list. So the confidence interval we're adding the one sample t interval, and the calculator command for that is t interval. And then we're going to do a one sample t test, and the calculator command for that is t test. So one sample t interval and one sample t test is what these are called. And if you go to stat over to the test, second one down is the t-test. And then if you go down to number 8, that's the t-interval. So those are the commands we'll be using. So before we get to actually making an interval and doing a test, what's different? Let's talk about the major difference between proportions and means. And the big difference is that we are going to use a new model for means. There's a better model that will get us to our confidence interval than the normal model, and it's called the t model, which is why it's called a one sample t interval and a one sample t test. And the thing about the t model is, I'm going to draw a couple models here. How does it compare to the normal model? Well, I'll make the normal model in kind of dark green here. And then I'm going to make the one t model in kind of light pink here. And these are not perfect here, but kind of highlight the difference. And then another t model. We're going to have a couple t models here. I'll kind of make this one a dotted one. Okay. So there are the models. We got a dotted line, we got a pink, and we got a green. So the green would be the normal model. And then the other two are two different t models. So you can see that the t model has more probability in the tails, fatter tails, and then less in the middle. So there's more spread in the t models. And I say t models because the t model will change depending on the sample size. So the smaller the sample, just kind of give some, and this is the, so let's say the solid pink is a t model with sample size 50. And then the dotted one is a t model with 500 sample size. So as the sample size increases, the t model becomes more and more like the normal model, and a t model with an infinite sample size actually becomes the normal model. And that is something you'll want to know about the t model. Know that it's unimodal symmetric, and know that it's more spread out, more probability in the tails, but then as n increases, as the sample size increases, it gets closer and closer to the normal model. We name t models by these things called degrees of freedom. The degrees of freedom, and the degrees of freedom, it's often a df, degrees of freedom, is n minus 1. N minus 1 are the degrees of freedom. So this pink one here, with 50, sample size 50, we would, if we had to name it, you would name it like this. It's not an n, it's a t, and then it's the T model with 49 degrees of freedom. So when you're making your distribution, and instead of an N now, we put a T, because it's not a normal model, T model. And then whenever you write a T, you want to say which T model, the T model with what sample size. And then again, we name them by these degrees of freedom, N minus 1. So if you have a sample size of 50, then you're using the T model with 49 degrees of freedom, N minus 1. So that's something to know. The degrees of freedom. What are the degrees of freedom? Well, they're N minus 1 for the T model, and the simplest definition would be they just tell you which T model you're using. So if you use a T model with sample size of 50, that's going to be the T model with 49 degrees of freedom. And then you'll see the T with the 49 right there. So when you see that 49, you know the sample size was 50 for that model. Okay? All right, now you're going to see the T a lot instead of the Z. So instead of a Z score, you're going to have a T score. Instead of using normal CDF, we're going to use T CDF, which is number 6, T CDF. Instead of using inverse T or inverse normal, we're going to use inverse T. And I think those are the main ones, the differences. So inverse normal is now inverse T. Normal CDF is now T CDF. When do we use the T's, the T model? When we're working with means. Means is not the normal model, it's this T model. And that's the big difference. That's the big difference you'll read about when you read chapter 23. All right, so let's just do a confidence interval and hypothesis test. And we're gonna start on page 557 and do number 32. Number 32, 557. So turn there, get your paper, calculator, pen or pencil out, and it is about Doritos. Some students checked 6 bags of Doritos marked with a net weight of 28.3 grams. So on the bag of Doritos, it says it should have 28.3 grams in there. They carefully weighed the contents of each bag, recording the following weights in grams. And then it lists 6 weights, 29.2, 28.5, 28.7. So we have a sample of size 6, okay? The bag says 28.3 grams, but is that correct? Is that true? What's the true mean weight for all these bags of Doritos? So we took a sample of size 6, and we're gonna make a 95% confidence interval for the mean weight of such bags. Okay, and so let's make that confidence interval, and let's do it using the calculator, kind of how you would do it on the AP test. Remember, you're going to name it, check the conditions, do it on the calculator, interpret the interval, done. That's all you need. After we do that, then we're going to kind of write out the formula, plug in everything in, kind of do it a little more, you might get a little more, kind of go through how to make the interval. Okay, so Part C, 32 Part C says create a 95% confidence interval for the mean weight of such bags of chips. So let's name it. We're going to make a 1 sample T interval. A 1 sample T interval. Name it. Great. Let's check our conditions. First condition for a 1 sample T interval is the random condition. Were these randomly selected, these 6 bags? And it says the students checked 6 bags of Doritos marked with a net weight. It doesn't say that it was a random sample or how are they sampled. So I'm going to put a question mark there, and I'm going to say the problem does not say how these bags were sampled, because they need to be randomly sampled. So the random condition, same as it's always been, it's got to be a random sample. And I put a question mark. Problem does not say how the bags were sampled, so we're not sure. Next, the independence 10% condition, same deal. The sample must be less than 10% of the population, and 6 bags of Doritos is definitely less than 10% of all bags of Doritos, so I'm going to write that down. 6 bags of Doritos are less than 10% of all bags of Doritos, the population. Give that a check. Okay, next up is the sample size condition, which is not success failure. So not the NP, NQ greater than or equal to 10. This is the sample size condition for means. And you may remember from chapter 18, we talked about the large enough sample condition. So I'm going to write that down, large enough sample. It's often called the nearly normal condition too, but they're both the same. You could say either one, large enough sample, nearly normal. And remember how this works. If the sample is below 15, it should be pretty unimodal symmetric to proceed. If the sample is between 15 and 30, then it doesn't have to be perfect. It could be a little skewed. It doesn't have to be, it could be a little off. And then if it's greater than 30, the shape of the distribution doesn't matter. It could look like anything, okay? So how are we gonna check this? If the sample size is less than 30, you've gotta make a histogram. You've gotta show that it is unimodal and symmetric enough to proceed. And that takes a little bit more work. You got to sketch out a histogram, use a scale. Use your calculator, okay? And then you look at it, and if it is unimodal symmetric, you say the sample is unimodal and symmetric enough with a small sample of whatever. It is unimodal and symmetric enough to proceed. If your sample is greater than 30, if your sample is like 35, 50, 100, then you don't need to make a histogram. You can just say the sample is large enough to proceed regardless of the shape of the sample. So that's nice when that happens. For us, though, our sample is only size 6. So you've got to make a histogram for the large enough sample condition. You've got to show that it's unimodal symmetric, because 6 is really small. So it should be unimodal symmetric. So here's what we do. We're going to put in our data. So you hit stat, enter, go to your list. I'm putting this into list 1. Sometimes they give you the stats of the sample, and then sometimes they give you just the data set. And this time they gave us the data set. So I'm putting that data into my list, those weights, 29.2, 28.5, 28.7, 28.9, 29.1, 29.5. All right, there they are in list 1. And I'm going to make a histogram now. So I go to stat plot, second y equals, plot 1 on, highlight the histogram. That's what I've got. Getting the data from list 1, zoom 9. Okay, and that doesn't look very unimodal symmetric. And sometimes you have to tinker with it, which is fine. Hold on. Okay, so when I do zoom 9, that's what I get. And remember, we only have 6 bags here. So you are allowed to tinker with this thing. And that's what we're going to do. So the lowest bag is 28.5. So I'm going to go from 28. The highest one is 29 or 29.5. 28 to 30. And just see what that looks like. So I'm just messing with my scale. I made it 28 to 30. All right, that looks not quite there yet. X, hold on, bear with me. That's pretty good. Well, all right, there we go. That looks unimodal. It's not totally symmetric, but it's pretty good. It's pretty good. Here was my window I used for that. Now, normally this isn't, you don't tinker with it that much to get there. I have a 28 to 30 and then 0.6 for my X scale. That one's tough because there are only six pieces in the data, but okay, so I'm gonna quick do a sketch of this. I hit the trace button, and then I just use that trace. The min is 28, to 28.6. You might have used a different scale, it's fine. And that goes from n equals 1. And then the next one is from 28.6 to 29.2. And then the next one is from 29.2 to 29.8, n equals 2. So a quick little sketch to show that it is unimodal and symmetric enough is what I did there. I hit the trace button, okay? Okay, so I'm gonna say with a small sample of size 6, so I'm acknowledging that it's a small sample. With a small sample of size 6, the sample is unimodal and symmetric enough to proceed. And give it a check. Okay, that's a little weird, I know, messing with the histogram, but you can do that. You can try to make it look unimodal symmetric. All right, so that's it. That's it. Those are our 3 conditions: random, 10%, large enough sample. So I'm going to say other than random. Oh, I'll say this: the random condition may not be met, so results may not be accurate. And those are our conditions. Okay, the random condition may not be met, so the results may not be accurate. All right, great. So let's make our interval. And first we're just going to do it on the calculator, which you are allowed to do on the AP test. So we're doing a t-interval. So go stat over to test, go down to number 8, t-interval. There we go, enter. Now, did we have the data, or did they give us the stats, like the mean and the standard deviation of our sample? They gave us the data, and we put the data in the list. So choose data. My data is in list 1, and the confidence level is 95%. So that's what I have for t-interval. I really didn't change anything. Data, and then 0.95, calculate, and there it is. So the interval is from 28.605 to 29.4. 28.6 to 29.4 is the interval. Now you've also, what else do you have to give? You've got to give the degrees of freedom. And the degrees of freedom here is 5. And that tells what T model you used. So you always want to give the degrees of freedom. Always give the degrees of freedom along with the interval. Okay, so there we go. Right off our calculator is our interval there. So we can say we are 95% confident that the true mean, and it says created 95% for the mean weight of Dorito bags. We are 95% confident that the true mean weight of Doritos is between 28.6 grams and 29.4 grams. We are 95% confident that the true mean weight of Doritos is between 28.6 grams and 29.4 grams. Sorry, my handwriting is bad, but it takes me forever to write it neat, and I'm saying it. I'll say it again so you guys can hear it and write it. Okay, that's all you need. Name, conditions, do it on your calculator, interpret it. Now, how did they actually make that 28.6 to 29.4? Let's quick run through that. So what makes up a confidence interval? It's the statistic, which used to be the p-hat, the sample proportion. Well, now it's the sample mean, Now it's the x bar instead of the p hat. The statistic, plus or minus the critical value, how many standard deviations we're reaching out, which was a z-score, but now it's a t-score. T-score, okay, times the standard deviation, which was square root pq over n, but now it's s over square root n. So what is that s over square root n? That is the standard deviation. It's actually the standard error because it's an estimation of the standard deviation of the sampling distribution, okay? So that used to be p hat plus or minus z for the critical value because it's a normal model times square root pq over n. Now it's s over square root n because we're in means now. And that is on your formula sheet, that s over square root n. Okay, so let's plug everything in. So where do we get the mean, the sample mean? Well, go to stat, one variable stats. On my list one are 6 Dorito bags, and that'll give you the sample mean. First one, 28.983. I'll just say 28.983 repeating. Plus or minus the t-score, not the z-score, the t-score. Now remember, how do you get that critical value? How many standard deviations we're reaching out? And we're 95, we want to be 95% confident. So that's 2.5% in each tail. So instead of doing inverse normal 0.025, we're going to do inverse t 0.025. Inverse t 0.025. And then, but what t model? Which t model are we using? And it's going to be 0.025, comma 5. So for all these t commands in our calculator, which t model? And it's the one with 5 degrees of freedom. 6 minus 1, 5. That will tell me how many standard deviations we're reaching out to be 95% confident. So here's my inverse t instead of inverse normal. Put your degrees of freedom in, and it is 2.5705. I'm going to say 05806. Okay, good. Times s over square root n. So what's the s? The s is the standard deviation of the sample, which we can get from one variable stats, where we got the sample mean from. So the one variable stats, the sx, that's what we want, the standard deviation of the sample, the sx, which is 0.3601. 0.3601 over square root n over square root 6. So this is everything plugged into the formula, and you might, actually you won't get a multiple choice this year, but you know, before they would have questions where you got to break down that formula. And let's crunch it out. I'm just going to quick crunch it out, see if it gives us the same interval. 0.3601 divided by square root 6 times 2.5706. That's the margin of error, 0.378. So it's like 28.98 plus or minus 0.378, 28.98 minus 0.378 is 28.6, nice. And then 28.98 plus 0.378 is 29.4. That's our confidence interval. All right, so that's where it comes from. That's what your calculator does for you when you put t interval in there, okay? And you don't need this on the AP test. If it's a free response, you only need that stuff, but you got to know that stuff, right? Okay, so that's the confidence interval. Now let's do a hypothesis test. And I know I wanted to keep these videos like 25 minutes, but you know, this is like, we got to talk through it. So they might go a little longer, but it's college level AP class. That's okay. All right, so we did number 32. Let's do number 30. Number 30, still on page 557, chapter 23, number 30. Now we're going to do a hypothesis test. So let's read it through. Company with a large fleet of cars hopes to keep gasoline costs down and sets a goal of a attaining a fleet average of at least 26 miles per gallon. All right, so they want to average at least 26 miles per gallon. To see if the goal is being met, they check the gasoline usage for 50 company trips chosen at random. All right, there's a sample size, n equals 50. Finding a mean, an x bar, a mean of 25.02 miles per gallon with a standard deviation, S, of 4.83 miles per gallon. Is this strong evidence that they have failed to attain their fuel economy goal? Okay, so note how this time n equals 50, but they didn't give us the 50 pieces of data. They gave us the stats, right? They just gave us the mean of the sample, the standard deviation of the sample, and that's all we need to do the test. So sometimes they give you all the data, and sometimes they don't. All right, so we're going to do a one sample t-test. Name it. One sample t-test. Now, their goal was averaging at least 26 miles per gallon. Okay, so the null hypothesis is that the true mean for this fleet of cars is 26 miles per gallon. And then the alternative is that the mean is, and we want to see, is this evidence that they have failed to attain their goal? So they got 25 miles per gallon in their sample, and they want at least 26. They want more miles. So we want to see, did they fail? Is this evidence that they failed? So is this evidence that it is less than 26 miles per gallon? It would be the alternative. And then define your mean, and that is the mean miles per gallon for their fleet of cars. The mean miles per gallon for this company's fleet of cars. That is the parameter of interest. What is the true mean? And is it less than 26? That's what they want it to be, less than 26 miles per gallon. Sorry if you can't read my handwriting there. Okay, so we named it. We wrote the hypotheses. Now let's check our conditions. So one, was it a random sample? And this time it did say random. They checked a random, yes. So problem states sample was random. Okay, two, 10%. Are 50 cars less than 10% of all cars at this company? And I guess not really sure how big the company is, so I'll put a question mark there. Not sure if 50 cars are less than 10% of all cars at this company. Okay, and then large enough sample. So again, let's just quick talk through large enough sample. If it's between 0 and 15, small sample, the sample has to be unimodal symmetric. Pretty unimodal symmetric. If it's between 15 and 30, it can be a little skewed, doesn't have to be perfect. Greater than 30, it can be bimodal, it can be heavily skewed, we're good to go. And the nice thing about this problem is that n equals 50. So no histogram necessary. You do not have to draw a histogram. And we don't even have the data to draw a histogram with. So we wouldn't even have been able to do that. So we're going to put a check by large enough sample, and we're going to say, and what I want you to get at in our sentence here is that, what are you checking for? We're checking to see if it's unimodal symmetric enough. But if it's greater than 30, it doesn't matter. So I'm going to say the sample is so large that its shape, I'll say, doesn't matter. How about? The sample is so large, and then I'll put in parentheses over 30, just kind of show them like what we're looking for. The sample is so large, over 30, that its shape doesn't matter. Check. And then I'll say, not sure if the 10% condition is met, so results may not be accurate. And you know, for this one, if you wanted to give 10% a check and say 50 cars are less than 10% of all cars for this company, check. And then you want to say check, 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 all conditions met. I think that would be totally fine for this problem. Okay, named it, hypotheses, conditions. Now we can do it on our calculator again. Let's do it on the calculator. Let's finish it like how we would do it on a free response question. Then we'll go and draw the sampling distribution, kind of show how it's done again. Okay, so this is t-test, second command there, t-test. Here we go. We don't have the data now. We don't have 50 pieces of data, but they gave us the stats. So you want to highlight stats there. Boom. Okay, what is the null? So the null is 26. Then under that, it has the x bar, the sample mean, 25.02. SX, the standard deviation, 4.83. And n equals 50. And then we want a greater or a less than. Is it less than 26? So choose the less than. So that's everything I have. All right. And let's calculate it. And I'll tell you what we need to report. Boom, there it is. So we need to give the t-score, the t equals. That's called the test statistic. That's like the z-score, right? It is a z-score, except we call it, they say t because it's a t model. It's a t-score. Then the p-value, you got to give the p-value, 0.0789886. And then you also need to give the degrees of freedom, which they don't give you on the calculator. They say n equals 50, but that would be 49 degrees of freedom. So those are the three things you need. You need the test statistic, the t-score. You need the p-value, and then you got to give the degrees of freedom. All right. And then we are done. We just need to state the conclusion. The p-value is 7.89%. How about we use alpha equals 0.05? So I'm going to say using alpha equals 0.05 with a p-value so high, we fail to reject the null. There is not sufficient evidence that the mean MPG for this company's cars is less than 26 miles per gallon. Read that again. So using alpha equals 0.05 with a p-value so high, 7.9%, we fail to reject the null. There is not sufficient evidence for the alternative. There is not sufficient evidence that the mean miles per gallon for this company's cars is less than 26 miles per gallon. Again, sorry for my handwriting, but you can play it over again and hear me say it. That's probably a better way to copy it down. All right, great. So the 25 miles per gallon didn't convince us that that it was less than 26 miles per gallon. It was pretty close. Okay. All right. So let's actually crunch out the p-value on our own. Make the sampling distribution. All right. So let's make the sampling distribution. All right. Where it's not the normal model, it's the T model. The T model with how many degrees of freedom? 49 degrees of freedom, n equals 50. Centered at the null, 26 miles per gallon. And then the standard deviation of the sampling distribution. That's the S over square root n, which is going to be 4.83 standard deviation of the sample, 4.83 over square root 50. Which is 0.683065. I don't like to round to my final answer. Okay, there we go. So there's my sampling distribution. T model, 49 degrees of freedom, centered at the null, 26, with my standard deviation there, my S over square root n, which is 0.683, okay? And then we want to see, so then our sample mean was 25.02, and then we're going less than that. Okay, so we need to find that at 25.02. What is that t-score, the z-score? How many standard deviations below the mean is that? So we're going to get a t-score now, not a z-score. Same thing though, how many standard deviations from the mean. So it's the value, 25.02, minus the mean, 26, divided by the standard deviation, that 0.683065. We'll see where that puts us. And I got negative 1.43471. So we are 1.4371 standard deviations below the mean there. That's my z-score, my t-score. And now we can get the probability, but we're not going to say normal CDF. We're going to say t-CDF. T-CDF. Lower bound, negative 99. Upper bound, our t-score, negative 1.43471. Another comma, and for all these inverse t-CDF, we always got to say what t model are we using. We're using the t model with 49 degrees of freedom. So for these commands, you can have an extra comma with your degrees of freedom. For your t-CDF, this is just like normal CDF here. Negative 99 to negative 1.4374, blah, blah, blah. So let's do our t-CDF and let's see if we get the same p-value. Here's what I type into t-CDF. And we get that 0.0788. That's the p-value we wanted. 0.0789. So there's the sampling distribution, getting our probability, not normal CDF, t-CDF, got to put your degrees of freedom in there, 49. New standard deviation formula, S over square root n instead of square root PQ over n. And that's it. That is a one sample t-test. Okay. Video is probably over 25 minutes, but that covers it. We're good. Got our confidence interval, got our hypothesis test for means, one sample. All right. Thanks, guys. Appreciate it.